Hi guys, in this video I want to talk to you about friction and do some sort of experiment, take some measurements to build your intuition for it. So to do that we're going to use a force sensor. It's hooked up to a computer. I can collect data. And you'll see that when I pull on this force sensor, it reads out a force. You may not be able to see it, but right now this is about -10 newtons. And when I push on it, the force kind of goes the other way. So this is what we're going to use to measure the force. And we're going to use some clever setups to kind of nail that friction. And I want to just get you to think about this scenario, like a box on a surface. When I'm applying a force and this box isn't moving, you can see that if I'm applying a force with 10 newtons, let's say in this direction, what is the force of friction opposing me? If it's not moving at all, if the object is not moving at all, I know it's at rest. I know the forces must be balanced. So if I push it with 10, friction is opposing me with 10. So that's something I can do to kind of measure friction for something that's at rest. And now if something is moving, let's say I'm pushing it with a force of 5 newtons in this direction. If it's moving at a constant velocity, so basically like a steady pace, I know that the 5 that I'm applying in this direction should balance out with friction opposing. So those force diagrams are going to look something like this. I drew tension here because I'm going to attach a string to these boxes, and really what the force sensor is going to be measuring is that force of tension. But I know that if it's moving at a constant velocity or if it's at rest, that the force of tension is equal to the force of friction. All this to say is what the force sensor here on the screen will read is equivalent to the component of force that is canceling out the force of friction. Okay, so let's clear this run. And get some data. So the first thing I want to show you is that the shape of this. That's like the most important thing. So when I apply a steady force, actually, can you predict what is the force going to look like when I pull, and then it starts to slip and move at constant velocity? What is that going to look like? If you've ever pushed an object across the floor, you might have some intuition with this. What do you think the force versus time graph is going to look like when I pull, and then it starts to slip? There's going to be 2 components to it. Pull. So right now, and then it starts to slip. I'm going to do it again. Pull. Over here, it's not moving at all, and then it starts to budge. And after it budges, it's basically a steady, constant force of friction. Pull, and then it starts to go the other direction, and then it's basically a constant force of friction. So I want to idealize this. Friction behaves as so. Here is when this object is at rest. At rest. We say that this is the force of static friction. And once this object moves, there is this force of kinetic friction. It is constant. And it's a steady value. So I haven't shown you this, but if you were to measure it, no matter whether the object is accelerating or moving at a higher velocity, constant velocity, the force of friction, this kinetic opposition, won't change. At least the effect of the surface. From air, that's a whole other effect. But from the surface, this opposition is independent of the velocity. But on the way, as it's at rest, static friction is going to oppose it until it starts to slip. This right here is the maximum value of the static force of friction. Let's see, I want to share with you 2 more little bits of data. So -12 is sort of the kinetic friction when there's 2 boxes. maybe a little bit hard to see, but if I double the mass of the object, let me just erase this. If I double the mass of the object, it's about 24. You may not be able to see it. But it's about, it scales with the mass. And now you might have a question, is the additional mass affecting the force of gravity? Is that what's different? And I want to say, no, it's not the force of gravity that's really affecting friction, it's something else. I just want to do one more run. Currently, kinetic friction about 12. That's the opposition. If I pull at an angle, the force of the sensor is roughly the same. The force from the sensor is roughly the same, but if you work out the free body diagram, you have tension at an angle, and so the component of tension as opposed to friction is less. Why did the component, so if the component of tension that needs to cancel out friction is less, that means friction is less. So why, when I pull at an angle, is friction less? It's because it's not the force of gravity that's changing when I pull at an angle. Can you figure it out what force is changing on this? It's not tension that's, it's not the horizontal component. It's not gravity, it's the normal force. When there's less mass pushing it down, there's less of an interaction with the surface. And so that's what's actually changing. It's the normal force. So we see here that the friction has that static bit, there's the kinetic bit, and it depends on the normal force. There's a few more things I'll talk about following on.